So in the last class we have calculated the magnetic moment or change in magnetic moment in an electron due to an externally applied magnetic field. We have also calculated the change in angular frequency caused by this external magnetic field, and further the change in frequency of the electron due to this external magnetic field, and an additional current caused by this change in frequency of the electron. And from this additional current we calculated the magnetic moment of each electron, of one electron, which is given here on the top. Magnetic moment, or the change in magnetic moment μm, equals minus e square r square b upon 4m, where b is the external magnetic field, e is the electronic charge, and r is the distance of the electron from the field axis, that is the z axis. We have applied field in the z axis, and r is the distance from the field axis, distance of the electron from the field axis, and m is the mass of the electron. Now for the whole atom we have to sum this term for all of the electrons. For all the electrons, E, B and M are constants. The only difference is R. So we sum it over all the R value, and we get the induced magnetic moment per atom. This term was for single electron, and now we will get the induced magnetic moment per atom, which is minus e square b upon 4m in summation r square. And summation r square can be written as z times average of r square. This is an approximation, and we have taken summation average of r square as the average or square root of average of r square as the average radius of electron from the field axis. Then if there are z number of electrons, if the atomic number is z, then multiplying the z with average of r square gives the summation r square term. It's an approximation. Now if the plane of the orbit of the electron lies in the xy plane, then average r square can be written as average of x square plus average of y square. And if r naught square, if the average of r naught square represents the average distance of the electron from the nucleus, average of r square was the average distance from the field axis, but average of r naught square is the average distance of electron from the nucleus. Now this is a three-dimensional space that electron occupies, so average of r naught square can be written as average of x square plus y square plus average of z square. Now if atom is spherically symmetrical, then average of x square equals average of y square equals average of z square. Now average of r square can be written as 2 times average of x square. From this equation, average of r square can be written as 2 times average of x square, since we have taken average of x square equal to average of y square, considering it to be symmetrical. Then similarly, average of r naught square can be written as 3 times, since there are 3 terms here and each of them are equal, considering the symmetry. Then average of r naught square is equal to 3 times average of x square. And dividing these two equations, we will get r naught square, average of r naught square upon average of r square equals 3 by 2. From this we can get average of r square as 2 by 3 times the average of r naught square. So we found the value of r square in terms, value of average of r square in terms of average of r naught square. So we can substitute this value in the equation for magnetic moment. Now, in place of summation r square, we know it can be replaced by z times the average of r square, where z is the number of electrons in the atom, and average of r square can be replaced by 2 by 3 times average of r naught square, which we have seen. And now, if there are capital N number of atoms per meter cube volume, then magnetization. Up to now, we have calculated the magnetic moment per atom. Now, if there are N number of atoms per meter cube volume, then magnetization can be written. What is magnetization? Magnetization is the magnetic moment per meter cube. How many magnetic moments are there per meter cube? That is magnetization. So, if N is the number of atoms per meter cube, we just have to multiply N, capital N, to the magnetic moment to get the magnetization. So, minus E square B Z N times average of R naught square upon 6n will give the magnetization. Now, B can be written as mu naught H using this, and minus E square mu naught H Zn average of R naught square upon 6n. Now, susceptibility can be written as magnetization upon H, which is equal to minus mu naught Z, H cancels, and E square capital N times average of R naught square upon 6n. So, this is the equation for diamagnetic susceptibility in Langevin theory. Now, finally concluding our points, we have obtained the Langevin's theory. We have studied the Langevin's theory, and we obtained the value of susceptibility for diamagnetic materials in Langevin's theory. And almost all the materials exhibit diamagnetism, though it is masked by other magnetic effects. And the susceptibility of a diamagnetic substance is directly proportional to the atomic number. That is, more the number of electrons, more will be the susceptibility. Since it is seen from this equation that diamagnetic susceptibility is directly proportional to the atomic number Z. The bigger would be the value of susceptibility if the atom is bigger. If the atom is bigger, the susceptibility will be bigger as well. Which, if atom is bigger, means its atomic number is higher. Atomic number higher means the susceptibility will be large. From the last equation, susceptibility depends on the internal structure of the atom, which is unchanged by the variation of temperature. So, susceptibility depends on the value of mu naught. Mu naught is the permeability, which in turn depends on the internal structure of the atom, of the material. And we know there is no dependence on temperature here. Diamagnetic susceptibility is independent of temperature. And in Langevin model, diamagnetism is attributed to the influence of the magnetic field on the orbital moment of the electrons. Although s electrons have zero angular moment in the absence of a magnetic field, yet they acquire a small amount of orbital momentum upon the application of the field. This explains why all the electrons in an atom contribute to diamagnetism. That is, we know that quantum mechanically, for s electrons, the angular momentum is zero. Since we know the value of angular momentum is given by root over L into L plus 1 times h cut, where L is the value of SPD values. So S value for S, L equals 0, F for S orbital, L equals 0, which means angular momentum is 0. But in case when an external magnetic field is applied, these s electrons as well acquire a small amount of orbital momentum upon the application of the field. So this explains why all the electrons in an atom contribute to diamagnetism.